Okay, so welcome everyone to my channel, which is the Jellyverse channel. In case you have not subscribed to the channel, make sure you do well to subscribe to it and get updated on each of the lessons in biochemistry, chemistry, physics, and also biology as well. So in this set of video, we are going to talk about the reactions of alkanes. You know that alkanes are actually saturated compounds. Saturated meaning they are not having any double bonds. Okay, so that's the meaning of the saturated, or their saturation level is high. There is no double bond inside. You get it? But now we are going to look at some of the basic reactions that alkanes go through. So the first one that we are supposed to talk about is the combustion reaction, where we are combining a hydrocarbon with oxygen to produce a carbon dioxide and water. But in this main video, we are going to talk about the halogenations of alkanes. Before we talk about halogenations of alkanes, I want us to emphasize on the type of cleavages that we have. We are having homolytic cleavage. So homolytic cleavage, and usually this type of cleavage occurs in molecules that are having the same electronegativity difference. For instance, if I'm having chlorine, because I'm doing halogenation, let me use the halogens to make things simple. A chlorine molecule, which is ClCl, or the same thing as the Cl2. This is a chlorine molecule, right? Now there's something I want you to focus here. In this bonding, right, we are having 2 electrons each. So let me try and zoom in. We are having 2 electrons in each. So this and this, we are having 2 electrons. Now, if there should be a cleavage or there should be a split, right, in this bond, then you should expect the electrons to be shared equally, because here it's a covalent bond. So if you are breaking the bond, each of them will take their electrons back and they are going to form radicals. So usually homolytic cleavages end up forming radicals. So radical formation, right? Radicals are very reactive. So radical formation. I want us to understand the basis of this before we start with the halogenation, either chlorination or bromination, right? And we are having, so you can have your Cl bonded to your Cl. If you are splitting the bond, you are going to have one of the electrons falling onto this and also one electron falling onto this. Now you can see the kind of arrows I'm using. If you are using this arrow, right, it means it's just one-headed arrow and it's just a movement of one electron. Okay, now if you are using 2, it means that there is a movement of 2 electrons. So I'm going to give you the fundamentals so that everything becomes easy. And usually this creates charges, especially negative charge. The one that is accepting the 2 electrons is a negative charge, but this one generates radicals. So this one occurs in heterolytic cleavage. So the heterolytic cleavage, for instance, if you're having oxygen and carbon, so heterolytic, where you are having carbon, let's say, bonded to oxygen or OH group. If you are breaking the bond between carbon and oxygen, oxygen is having a higher electronegativity difference. So you don't expect the electrons to be shared equally, but all the electrons will move on to oxygen. And now it's going to generate something like a carbon with a positive charge. And that's what they're referring to as a carbocation, right? Let me specify it here. Carbocation. The cation means a positive charge, and carb, so mean a carbon with a positive charge. And then you're going to get your OH minus. This is the one that receives all the electrons because it's the oxygen that's having the highest electronegativity between the carbon and the oxygen in this bonding, right? So now this one is hetero because it creates charges among themselves. It's not radicals. Now let's move on to the main thing. in terms of ionic reaction, right? Ionic reaction proceed with the electrolytic cleavage, like what you are seeing here, having a positive charge and also a negative charge, where one atom takes all the shared electrons while the other also leaves with an empty orbital. So if you want to look at the structure of this, for instance, if you want to look at a carbocation, a carbon, let me just give you a scenario here. Okay, if you're having a carbon bonded to OH group, you are also having let's say CH3. Here you are having hydrogen, and on this side you are having bromine. Okay, if this is your structure and you are having a cleavage and oxygen is taking all the electrons, you are going to generate a carbon, all right, but this carbon will now be assuming the sp3, okay, where you are having your Br, you are having your hydrogen, you are having your CH3, and now it's having an empty orbital. You know how p orbital looks like a dumbbell. So this is how it will look like, and there is nothing inside, so the positive charge can be here, or you can put the positive charge here. This is a carbocation. So carbocation. Right. Now let's try and move into the radical formation. Now there are some compounds that are referred to as the radical initiators. So the moment you start with the halogenation, let's start with chlorination of alkanes. Okay, that is the addition of chlorines. So chlorination of alkane. This alkane, let's take the simplest alkane, that is the methane, right? So chlorination of methane. Now radical reactions are actually divided into three main steps, okay, where we are having the first one to be the initiation. It is in this particular step that you are going to generate your radicals. So always don't forget, followed by propagation. That is where you are going to have all your hydrogens, or your hydrogens be replaced by the chlorine molecules or the halogen molecule. So propagation. And the third step is the termination, where you are having two radicals coming together to terminate the reaction. So termination. All right, now this sounds very simple. So now let's start with the initiation. So the initiation, what goes into it? For instance, if you are dealing with chlorine, right, you can have just a simple catalyst, or you can have a simple condition generating your radicals. For instance, if you are having chlorine also bonded to chlorine, right, let me use my short ruler, chlorine also bonded to chlorine, you can, in the presence of heat or sunlight, you can have them splitting. So in the presence of heat, right, or even sunlight, which is HV, you can have these electrons splitting homolytically, where one electron goes onto this side and also another electron moves here, and then you are going to generate a radical and also another radical. So this one I can still rewrite it as 2 chlorine radicals, which is 2Cl dot. Very simple, right? So these are our radicals. These are very reactive. So reactive species. The moment you form radicals, they are having a high amount of energy, so they are reactive in nature. Now let's try and look at the propagation, because the propagation is the most important thing. Like I told you, the halogenation reaction or halogenation of alkanes is involved in 3 steps: initiation, propagation, and also termination. So now let's move straight into the propagation step, where the new radicals that have been generated are now attacking the hydrogens. And remember, for us to generate our radicals, we are also having something called the radical initiators. So one of the most common radical initiator that we usually use is the AIBN, and the AIBN is the same thing as the you are having your azo, and now you move to the azo base, right? Then we move to the I, which is the iso. Then we move to the B, which is the butyro. So butyro, and then move to the N, which is the nitrile. So you see how I've broken everything down. You can decide not to remember this, and also just remember the acronym, which is the I, AI, B, N. That's also a radical initiator. Now let's move on to the mechanisms that involves in the halogenation of alkanes, especially we are using chlorine. So let me write my methane here. So methane, a hydrogen, 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 and also a hydrogen. I'm in the propagation stage, so let me try and indicate its propagation. Okay, so I'm going to have one of the chlorine radicals, dot, right? It's very reactive, so it's going to take, it's bringing one electron. So as you can see, this is what I'm doing. The hydrogen also bring it one electron here. You get it. Then the bonded electrons, one of the electrons will also go on to carbon. You see how simple I've taken it. Chlorine will bring its electron by attacking the hydrogen. Hydrogen also bring its bonding electron from this side. Now it's converged at 2 electrons, meaning it can form a bond, which is the HCl. Then the remaining 1 electron from this bonding electrons will then fall onto carbon. So now you are going to generate a new radical from the methane side. So you are going to form H, C, H, and I will form a dot here, right? This is the radical that I'm talking about, plus your HCl. You are going to form HCl from what you had here, because chlorine and hydrogen, they come together to give you HCl. Now this radical, okay, let me move on and try and indicate the radical. As time goes on, I will not be taking time to be drawing the radical because you'll be familiar with it. Now hydrogen bonded to carbon, bonded to hydrogen, bonded to hydrogen, dots, right? It can now attack chlorine molecule. So it can attack this chlorine molecule by bringing 1 electron. Chlorine also bring its 1 electron, and then the other electron that they are sharing, the bond electrons, will go onto this chlorine. You get it? So now we are going to form a chloromethane. So you see how we are replacing all the hydrogens by chlorine one by one. Hydrogen here, hydrogen, and also chlorine, right? Now you are going to have 1 chlorine radical somewhere hiding here. This chlorine radical can attack another hydrogen here by bringing 1. This one can also bring another 1, right? And the bonding electrons, carbon will also take its part of the 1 electron. And now you see it is removing this hydrogen from there. We are going to have hydrogen bonded to carbon, bonded to chlorine, hydrogen, and then we are having a radical here. So now this one also becomes another radical. We are using the arrow so that we understand the mechanism very, very, very well. Now you are going to have another chlorine, right? So this radical can actually attack, and chlorine will also bring it 1 electron, and then the other electron will go onto this. You see how beautiful it is. If you understand the arrows, things are very simple. Then you are going to generate a carbon bonded to chlorine. You are having another chlorine here, and then hydrogen. So if the question specifies that write the propagation mechanism for halogenation of a methane to form dichloromethane, you end it here. Then you move to the termination. When you get to the termination, I will show you how to do it. But if it asks you to write the propagation mechanism for the formation of tetrachloromethane, it means that all the hydrogens have been replaced with chlorine. So you have to still move on. So I'm moving on to the last step so that at least you understand everything. Now I'm going to have chlorine. So chlorine radical can attack a hydrogen here by bringing 1 electron. This one also attack it by bringing one electron, and then the other electron will fall into this carbon. So you see, so now you are going to have our carbon radical Cl, and a hydrogen, right? And now you are going to have, so remember, whenever you are having a chlorine radical and a hydrogen, they form HCl. I'm not indicating it because I want the final product. So I'm going to have this radical. This radical can also attack chlorine molecules. And now, to bring one here, this one also bring its one electron, and then this chlorine will take its share. You see, so the reaction continues. Now you have replaced 3 hydrogens, right, with chlorine. So you are going to have chlorine bonded to carbon, bonded to chlorine, bonded to hydrogen, and now it's bonded to chlorine. So now we are having trichloromethane. So then we move on. Remember, you are going to have a radical, chlorine radical here. This chlorine radical can attack the hydrogen. This hydrogen also brings its one electron, and the remaining will also go here. And now we are going to form a radical that is made up of only carbon and chlorine. So chlorine, carbon, chlorine, chlorine, and now there's a radical here. So now this radical is just a reactive species. Guess what it can do? It can actually attack chlorine molecule. Then it means all the hydrogens have been replaced. This one will bring one. This one also will bring one, and then the remaining electrons will go onto this side. So now see the last thing I'm doing. I'm coming to form my carbon with chlorine, 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 and also chlorine. So now I'll form my tetrachloromethane. Right, this is my tetrachloromethane, where all my hydrogens have been replaced with chlorine. It is tetra because I'm having 4 chlorine molecules attached to the same carbon. Now let's go to the termination stage. The termination is one of the fascinating parts. If you really understand what you are doing, things. So I'm going to show you the shortcut for the termination reaction, or the termination stage. Right, for the termination stage, just add any two radical that you can see. So you can, because here all the hydrogens have been replaced with chlorine, you can just add a chlorine radical and also a chlorine radical. This one, they are not splitting, they are forming the bond. So one will come here, and also the other one will also come here, and then they form Cl2. Cl2 is just a neutral species, right? It's not reactive. So radical coming together, it will reduce the energy of the compound, and it becomes a stable compound. So it will not be reactive unless it is being split up again by sunlight or heat in the presence of your radical initiators, such as the azobase isobutylnitro or the AIBN. So you can also add another radical. Remember, you are having a lot of radicals. You can add maybe your chlorine, the carbon that was having the radical can have this, can add a lot of them, and you are going to get, let's say you are having this chlorine, right? You can also add another radical, which is maybe hydrogen, C, hydrogen, and maybe Cl, also radical. At the end of the day, this carbon will bring its one electron here. This one also bring its one electron, and we are going to form a carbon bonded to carbon, where this carbon we are having hydrogen, hydrogen, chlorine. On this carbon too, we are having chlorine, hydrogen, chlorine. So very simple. You can just add any two radicals together to terminate the reaction. Now, if you understand this thing very well, you can actually do the chlorination or bromination. The bromination also follows the same thing. At the end of the day, it is a halogenation of alkanes. So bromination also follows the same step. And if you want to go further, you can also use let's say propane, where you are replacing all the hydrogens with chlorine or bromine molecules. Now that brings us to the end of the halogenation of alkanes, because now we have the strong foundation about this particular step. So let's do the final thing here, or the final summary, from initiation all the way to propagation, then all the way to termination. Alright, so that brings us to the end of the reaction mechanism for halogenations of alkanes. So the next thing that we are going to look out for is probably the energy dynamics. Now when two radicals come together, let me add this last information, then I end the lessons. If you are having your energy, that profile diagram to be this, right? When two radicals come together, remember, let's say you are having radical 1 and also radical 2. All these things are having high amount of energy, so let's say they will be around this point, right? When these two things come together, and then you are going to have your energy is going to come down. You are going to have Cl2, meaning the Cl2 is what most stable, but this one is actually very reactive and it is unstable. You get it? So that brings us to the end of the lesson for the halogenation of alkane. We've done all these things. We've talked about carbocation, chlorination. We talked about the initiation steps. We talked about also the azo-base isobutyronitrate, which is the radical initiator. We've also talked about the propagation stage. Following all these things will make you understand whatever that you do. So this is the radical. You see how we are using only one arrow throughout. You can't use two arrows because there is no movement of two electrons. You have to use only one arrow because there is always a transfer of one electrons when you are breaking or you are forming the bond. Alright, and that brings us to the end of this video lessons. Make sure you do what to subscribe to my channel, and don't forget to hit the like button and also comment on it on any part that I didn't understand. Me seeing the message is my top priority to also do another video that will make you understand it perfectly. Alright, have a great day, you all.